Hello everyone, welcome to the opening video on Laplace transform. A Laplace transform is an integral transform. That means what we do is take a function of some variable and then via some sort of an integral we take that function to another form of a function in another space where the intended problem we are supposed to solve may be expressed in an easier version. And then what we do is that we take that function back to the original function after solving it in the easier space or easier form to the original version via some inverse transform, and preferably interpret our solution there which matches the required solution. So if it doesn't make sense too much, it will eventually after you have gone through this set of videos. What I intend to do is to give you a basic understanding and the processes of Laplace transformation for cases where you might need to understand these topics in kind of an accelerated manner. So what I intend to do in these videos is simply to show you the calculational aspect, number one, and number two, show you the cases of application where this Laplace transformation comes in handy, which will motivate you to learn this topic even more. Remember, my job is to give you the primary exposure. Of course, once the foundation has been established, you can always build upon that. So here we have a formula where we have this function f of t, which is in a space of variable t, the function capital F, and we're supposed to take its Laplace transformation. The Laplace transformation, or this integral here, which is written as the integration of f of t while multiplied with this function e to the power negative st, and then integrating it from 0 to infinity, will take us to another space, which is the space of variable s. And we get a new form for our function, which is small f of s. And this small f of s is what we dub as the Laplace transformation of capital F of t. Now, as you can assume, this e to the power negative st is suppressing the function f of t dt, well, dt is not the part of the function, but f of t really strongly, and therefore we may expect the integral from 0 to infinity may exist. However, it might be the case that the suppression by e to the power negative st is not as strong as f of t, in which case there might not be a Laplace transformation at all. So the Laplace transformation is not always guaranteed. So let us look at the cases which gives us the sufficient condition for the existence of Laplace transform, and under which condition they might be violated, and then what can we expect. So here I describe the condition for Laplace transformation to exist. It turns out, and expectedly, the existence of Laplace transformation means the convergence of this integral. Of course, anytime we have an integral, the primary and utmost important thing that we need to talk about is the convergence of that integral. Otherwise, it is probably meaningless to talk about it. What do we mean by convergence? Convergence means it gives us a result. It goes toward a finite result. That's what we mean by convergence. So this integral will probably give us a function, finite function, or at least finite in some designated places that we're interested in. So the question really boils down to the conditions under which this convergence occur. So one thing we can say about for sure is the set of sufficient conditions for this integral to converge. And there are two conditions. Number one, the function f of t, this capital F of t, this right here, whose Laplace transformation we are supposed to take, is at least sectionally continuous, or in other words, piecewise continuous for finite interval with a limit. So it's from 0 to n. This function is at least piecewise or sectionally continuous. What it means, we shall talk about it in a minute. And the second condition that is necessary is that this function f of t after this interval, that means after n, or in other words when t gets bigger than n, must be of an exponential order gamma. What that means is also needs to be explained. So as promised, let us first see an example of sectionally or piecewise continuous function. A function which is sectionally or piecewise continuous is defined in an interval. So in this case, the function is defined within the interval from alpha to beta, and the function is drawn in red. This function f of t is piecewise continuous if the interval from alpha to beta, can be subdivided into a finite number of subintervals. So for example, let me call this value as t1 and this value as t2. So we have divided the function into 3 subintervals, the first one being from alpha to t1, the second one being from t1 to t2, and the third one being from t2 to beta. So if the interval can be subdivided into a finite number of intervals, in each of which the function is continuous. As you can see, the function f of t is continuous within each of these intervals and has a finite left-hand and right-hand limit. That means within these intervals, the function doesn't blow up. And so therefore, within these intervals, the function does have limit, but also at the endpoints or the interval points, for example here in t1, t2, or alpha, beta for that matter, none of these functions blow up, and at t1 and at t2, the points of the subinterval, the left-hand limit, which is this one, and the right-hand limit, which is this one, both of them are finite. The same goes for this one as well. The left-hand limit and the right-hand limit are finite. Even though they don't match, but they are finite. So that's the example of sectionally or piecewise continuous functions. Now let's go on to see an example or different examples of functions of exponential order. So here are 2 examples which we shall be using to explain the concept of functions of exponential order. But before that, let us define what does it mean by this concept. A function, let's say f of t, this function is of exponential order if there exists a number n, and when t gets bigger than n, then this f, or the absolute value of f, is bound by this particular form of function, which is m, which is a constant, and then e to the power gamma t. If this is the case, then f of t is called a function of exponential order gamma, right, as t tends to infinity. So once again, there exists a number, capital N, and t has to be bigger than this n. So n is sort of the lowest limit beyond which the exhibition of this property is not necessary. So as t gets bigger and bigger than n, then f of t is less than this exponential growth e to the power gamma t times a number capital M. So here I do have 2 examples. One is in here where f of t is equal to t squared, and the second one is f of t equals e to the power t squared. So one is t squared and the other one is e to the power t squared. And our job is to understand whether these functions are of exponential order, and if they are, then what is their exponential order. So the first one being f of t equal to t squared, this is a function of exponential order, specifically order 3. Why? Because t squared is always smaller than e to the power 3t. Specifically, its absolute value is smaller than e to the power 3t as soon as we get t greater than 0. So in this case, our capital M is 1. So this is 1. And gamma is 3. And this n is 0. Okay? Another familiar way or equivalent way to check this same property by taking this e to the power gamma t factor to the other side and then see if that is bounded by some number m. So basically what I'm saying is multiply f of t with e to the power negative gamma t and take the absolute value and see if it is bounded by some number as t gets to infinity. And this is certainly useful in this case, the case B, where we have e to the power t squared minus gamma t. So if I multiply e to the power t squared by e to the power negative gamma t, then we get this number, and this number, when the absolute value taken, is actually gets bigger and bigger as t grows bigger. So this goes to infinity as t goes to infinity. So there is no upper bound. So this function is not a function of exponential order. So I think the idea is clear now. The next step for us is to determine or compute actually the Laplace transformations of some functions.